I'm going to have to stop and fix a couple of things here. Okay, a few touch-ups here. The vertical line, I was going to write the equation of the line, but that was going to get too complicated, have to parameterize it and so forth. The vertical line above x, y is 0 intersects the sphere at least once. Now, almost everywhere it intersects twice, but when you get out to the boundary of the circle, x squared plus y squared equals 1, you have only one intersection point. So, now, as long as x squared plus y squared is less than or equal to 1, vertical line intersects the sphere at least once. If x squared plus y squared isn't less than or equal to 1, you can't have a point, you can't find a z point. If x squared plus y squared is greater than or equal to 1, there's no z that makes this 1. Okay, so that our region in the first octant is bounded by x squared plus y squared equals 1, circle of radius 1. Now, given that this object is a sphere, it's a sphere of radius 1 sitting on the origin, it is fairly intuitively obvious that part of that sphere lies above the circle of radius 1 in the xy plane. None of the sphere lies above any point outside that circle. For any point inside that circle, you're going to have 2 points of intersection. It isn't hard to see that intuitively, but for a lot of surfaces, we're going to have to do a little more analysis. So I've illustrated just one possible line of reasoning here. By the same sort of reasoning we've used previously, we see that this surface, this sphere that I haven't drawn very well because I've wanted to do some labeling, but let's go ahead and draw some contour lines to make the thing halfway plausible. Okay, it looks pretty bad down here. It looks like a waning moon. Mostly because of the distortion of the axes here, and I probably should have started that over when I realized that was happening. However, okay, we know then that our region can be described as 0 less than or equal to x less than or equal to 1, corresponding to partition of this x interval from 0 to x equals 0 to x equals 1, and then from 0 to y to the square root of 1 minus x squared. This bounding circle is the same as the circle of intersection we had in the preceding example where the sphere actually intersected the xy plane. And then our z. Now let's consider this. For a given xy, z minus 1 squared equals 1 minus x squared minus y squared. Now let's just work out the algebra of that very quickly. Okay, so if we have z minus 1 squared equals 1 minus x squared minus y squared, then z minus 1 is plus or minus the square root of 1 minus x squared minus y squared. Now z is never less than 0. So if we have an xy within this circle, that means we're going to get 2 possible values of z. One corresponding to the plus, one corresponding to the minus. The solution is pretty straightforward. Z then equals 1 plus or minus the square root of 1 minus x squared minus y squared. that corresponds well enough with the geometry. I'm not going to try to draw this. I've already messed up the drawing badly enough. But the z equals 1 plane cuts this sphere in half. The upper half, there will be a point lying above the plane. On the lower half, there will be a point lying the same distance below the plane. That distance is square root of 1 minus x squared minus y squared. The z points are therefore 1 plus the square root of 1 minus x squared minus y squared and 1 minus the square root of 1 minus x squared minus y squared. It is getting a little late, but I should know better. I wrote a 0 here without thinking because that's what we did before, so I have to fix that. And there is no surface between z equals 0 and z equals 1 minus the square root of x squared, 1 minus x squared minus y squared. The surface doesn't start until we hit the point where z equals 1 minus the square root of 1 minus x squared minus y squared. So that what I should have written here is 1 minus the square root of 1 minus x squared minus y squared is less than or equal to z, and that is less than or equal to the 1 plus square root of x. Darn. Okay, sorry, but I had to fix that. Okay, z goes from 1 minus the square root to 1 plus the square root. For those values of z, we're inside this awful looking sphere. Without going through all the details of the summation and so forth, because we really don't want to have to go through that on every problem as long as we understand it, we see that if we want to integrate a function, f of x, y, z, over this part of our sphere, our integral is going to be what? Well, here are the inequalities that describe our x and y and z. So we're going to have a triple integral. If our function that we're integrating is f of x, y, z in general, then we'll integrate z first between these limits. Now the limits are 1 minus the square root of 1 minus x squared minus y squared and 1 plus the square root of 1 minus x squared minus y squared. Those are the limits on our z. Now I'm going to switch colors so we can keep track of what's what here. And then we integrate y from 0 to 1 minus x squared. And finally, we integrate x just from 0 to 1. And that's our integral. We haven't yet given examples where we evaluate integrals of this type, but examples will follow. And of course, both of these surfaces are spheres, but they nicely illustrate some of the main properties that some of the main problems and properties encountered with triple integrals over three-dimensional regions. Forgive the errors and the patches. It is getting late, and regrettably, I'm going to have to tear myself away from the sound of my own voice and sign off until tomorrow.